Hey everyone, and welcome back to The Explainer. Today we are going on an absolutely massive conceptual journey. Seriously, we're going to connect the invisible digital data sitting right there in your pocket to the mathematical foundation that governs the ultimate inescapable fate of the entire universe. I know, it sounds like science fiction, but it's actually pure mathematical fact. Okay, let's just dive right into our roadmap. We'll start with the mathematics of surprise, then move into how we compress our digital world, reveal a massive thermodynamic plot twist, rewind all the way back to the low-entropy Big Bang, and finally, look ahead to the ultimate heat death of the universe. All right, Section 1, the mathematics of surprise. To wrap our heads around the fate of the cosmos, we actually need to start really small, by scaling down to a highly relatable micro-level concept that we experience every single day. So, how do you actually measure a surprise? It's a feeling, right? It's a very human emotion tied to uncertainty. But what if I told you that uncertainty has a strict, measurable mathematical value? Let's look at how we calculate the exact weight of not knowing what happens next. Think about it like this. If I flip a double-headed coin, you know for a fact it's going to land on heads. The probability is 100%. Because you already know the outcome, watching that coin land gives you absolutely zero new information. There's zero surprise. But if I flip a perfectly fair coin, you're in a state of maximum uncertainty. It could be heads, could be tails. When that coin finally lands, resolving that uncertainty gives you exactly one full bit of data. So a predictable outcome yields zero information, while a totally uncertain outcome actually generates information. The crucial point here is that this measurement of missing information has a name. It's called information entropy. It was introduced by Claude Shannon in his legendary 1948 paper. Now, entropy isn't just a metaphor for a teenager's messy bedroom. In information theory, it's the strict mathematical quantification of uncertainty. The more uncertain an event, the higher its information entropy. When the entropy is zero, there's no freedom of choice, and therefore no new information is being conveyed to you. Which leads us nicely into Section 2, compressing our digital world. Let's see how Shannon's entropy is built into the technology we use every single day to communicate. Claude Shannon realized something absolutely mind-blowing about human communication. Our languages actually have very low entropy. Take English, for example. It's highly predictable. If you see the letter Q, you can almost guarantee the next letter is going to be a U, and the letter Z, incredibly rare compared to E. Because of this predictability, English text only contains about 0.6 to 1.3 bits of actual entropy per character. The rest is just structural redundancy. Shannon mathematically proved that if you remove this predictable redundancy, you can compress data incredibly tightly without losing a single drop of the original message. It is just fascinating to look at the sheer scale of what Shannon's discovery enabled. Because we understand how to squeeze out that low entropy redundancy, humankind has been able to store and broadcast mind-boggling amounts of data. By the year 2007, we were globally storing 295 entropically compressed exabytes of data and broadcasting 1,900 exabytes. This mathematical compression is for sure the invisible engine powering the entire digital age. And now, we hit Section 3, the thermodynamic plot twist. This is the massive cosmic twist of our explainer, where computer science unexpectedly, violently collides with astrophysics. Long before Claude Shannon was even born, 19th century physicists like Lord Kelvin were busy studying steam engines and heat. Kelvin helped formulate the Second Law of Thermodynamics, realizing that mechanical energy naturally tends to dissipate into unusable heat. Extrapolating this to the cosmos, he wrote back in 1862 that the result would inevitably be a state of universal rest and death if the universe were finite and left to obey existing laws. Basically, Kelvin realized that if heat is constantly lost and dissipating, the entire universe must be winding down like a giant exhausted clock until all useful energy is just... And here is the incredible reveal. Take a look at this. On one side, we have Claude Shannon's 1948 formula for information entropy, measuring digital surprise in bits of data. On the other, we have the Gibbs entropy formula, which built on Ludwig Boltzmann's work in classical thermodynamics to measure the physical disorder of microscopic particles in the universe. Notice anything? They're structurally identical. Shannon and the classical physicists stumbled upon the exact same underlying mathematical formula. The math that dictates how much you can compress a text message is the exact same math dictating the physical decay of energy in the cosmos. Information and physical reality are bound by the exact same laws. Section 4, the low-entropy Big Bang. Armed with the knowledge that information and physical reality share this deep, underlying link, let's rewind the clock all the way to the very beginning of everything. If the universe is constantly moving towards higher entropy, meaning more disorder, more missing information, then to have a forward-moving arrow of time, the universe had to start in a highly structured, perfectly low entropy state. The physicist Roger Penrose proposed the Weyl curvature hypothesis to explain this. He posited that at the Big Bang, the universe had a vanishing Weyl tensor. Now, in simple non-physics PhD terms, that just means the initial state of the universe was a perfectly smooth, extraordinarily low entropy clean slate. No clumps, no chaos, just perfect order. So let's walk through how this clean slate evolved. First, the universe expands rapidly from this highly structured, low entropy starting line. Second, as it expands, quantum fluctuations undergo what physicists call mode squeezing, which is essentially quantum states getting tightly compressed to produce quantum entanglement. Third, as matter clumps together to form galaxies and black holes, gravitational entropy massively grows. This constant, unstoppable increase in entropy is literally what creates the thermodynamic arrow of time. It's the whole reason why you remember the past but not the future. Which brings us to our final stop, Section 5, the ultimate heat death. We're going to look way, way ahead to the very end of this one-way timeline of increasing entropy. 10 to the power of 100 years, also known as a googol. This is a staggeringly incomprehensible timescale. Trillions of years after the last stars have burned out and the universe has gone completely dark, the only things left will be supermassive black holes. And you know what? Even they can't escape entropy. Over the course of 10 to the power of 100 years, these gargantuan black holes will slowly leak energy via Hawking radiation until they completely evaporate into nothingness. Once those last black holes evaporate, we arrive at the heat death, or the big freeze. This is when the universe hits maximum entropy. The cosmic coin has been flipped so many times that everything is just uniform. Energy is entirely, evenly dispersed. The universe reaches total thermodynamic equilibrium. Because there are no longer any differences in temperature or energy anywhere, no further physical work is possible. It is completely unpredictable, totally uniform, and essentially dead. But before we wrap up, I want to leave you with a final, slightly provocative thought. When the universe reaches this state of maximum entropy, when it's just a vast, cold, empty soup of evenly distributed photons, is that really the end? Some physicists hypothesize that in a system left alone for vast, almost infinite periods of time, thermal fluctuations and quantum tunneling could occur. A spontaneous decrease in entropy could just happen, meaning this dead high-entropy universe might actually just be the necessary quiet setup for a massive quantum fluctuation to spark a brand new Big Bang, starting the whole beautiful mathematical cycle all over again. Thank you so much for exploring the cosmos with me today. Stay curious.